And record. Perfect. Let's see. Catching up with chat, guys. Bear with me for a second. Yeah, so John Dean gave a pretty good explanation. So you do fold, and only elements that match your filter will stay in kind of your new list. So the idea, it's not a combination of fold and filter. You're not like, filter is a type of fold. That's the idea. So you're defining filter in terms of fold now. That's as much as I will go into that, I think. If you have more questions, set up office hours, and we're happy to kind of show you where to start, that kind of stuff. But I don't want fold to hijack the whole class again today. We did that yesterday. So any other questions before we jump into the new material today? Cool. And I know a few people were signing in or walking in the room when I said it. The quiz for today will be posted after class. I have to write it still. I don't know where we'll get today. And what did I say right before that? Remind me. It was some other logistics thing. Oh, I didn't hold my office hours today. They'll be tomorrow, probably 3 o'clock. Keep an eye on Canvas for an announcement about that. So thanks for bearing with me there. I had something come up I had to do at 3 today. Otherwise, I think we're good to jump into the new material. If you have other questions, go and say so in chat. Otherwise, let's get started. So as you guys have probably read, we're starting our discussion of programming languages as kind of an object of study now. So instead of looking at small functional programs, we're thinking about programming languages as a whole. How do we design them? Where do we start with that? It seems like this kind of Herculean task that would seem really hard to do. Like, how do you write C? Okay, well, it'd take 30 PhDs to even start to answer that question, right? And I mean individual people, right? There's a lot of moving parts, but how do we get started with that? Well, it's usually one person sits down, starts to sketch out a language, how they'd like to write programs, and they give it some syntax, some symbols. They start to give it some meaning, how does this thing evaluate? What's the semantics of it? And we'll revisit these ideas a lot, but the idea is that we actually start to chip away at this. So we're going to start by defining a really small core language, start throwing on new features in the same way you develop software. It's no different, but it's given a linguistic approach. So yeah, so let's jump into this. So here's an example of a language I want to talk about today. Just an easy introduction. We'll kind of revisit this language, this toy language, a few times throughout the class. Here's a couple in the green, couple of examples of a program, finger quotes there. What do we typically call this programming language? Kind of math, but more specifically, right? Does anyone know the name of kind of numbers and operations on numbers?
Algebra?
Not quite algebra. Algebra's works on top of this, I think, strictly speaking. Or algebra is when I start throwing symbols into it. Yeah, Brian comes in with it. It's called arithmetic, right? So this is like arithmetic. It's just numbers, just small operations like plus, minus, multiply. Powers are sometimes thrown in there. I'll often call it arithmetic in the adjective form too. So if that throws anybody off, this is the arithmetic language, or the language of arithmetic. Is how we'll talk about it. But how do we define it? Let's actually define this language, and later we'll kind of augment it with variables. We could do algebra on it, which actually might be an interesting kind of side problem on the homeworks, maybe a bonus kind of thing, is how do we define algebra on this? Could we define solvers maybe? But let's start here, right? Do these programs, these 4 examples, I guess, do they evaluate to anything? Yeah, so they all evaluate to natural numbers, right? What are the particular natural numbers, right? So we all kind of know this answer, but it bears kind of discussing. Ooh, I don't like it how it stretches that. Is there a way to make that not do that? I don't think so. If anyone knows how whatever this app is called works, tell me if there's a way for me not to stretch this, but for now we'll just stretch it. 1 equals 1 if we were to kind of evaluate it. There are no operations in there. It's kind of a value, an answer, right? 5 is 10. 7 times 8 is 56, I hope. 4 minus 2 is 2. Simple, right? Yeah, it's pseudo. I think that's the right answer. I need to move it off the white space and then do it. I'm not going to do that. That's okay. Yeah, so we can kind of evaluate these expressions. That's a property of the language, is they have an evaluation or kind of a meaning, right? So I'll often talk about kind of 2 parts of kind of the language pie, I guess. And we'll call these kind of syntax and semantics. I think we talked about this a little bit in the first week. What's the syntax of this language? And by syntax, I mean the symbols and structure of the language. So what might I expect here? Yeah, so a bunch of answers in chat. Stuff like plus, multiply, minus, and divide. So we'll call these operations, right? What else might we see? So Graham says like numerals 0 through 9, right? Yeah, so numbers. I'll write numbers for now. We could use numerals. We're going to end up using the natural numbers as we've already defined them. Multiply. John Dean, I don't know what that other symbol you're trying to use means in this context, if you could elaborate. Ben asks, is equality an operation? It could be, but we won't have it be yet. That'll come a little later, but I do like how you're thinking. Yeah, so what might, this is the syntax. We also talk about the semantics, right? So the other big part of the language pie is semantics. This is the meaning of a program. Okay, so this is stuff like, what does it evaluate to? Is it well typed? If there's a type system, is it type safe, right? Another thing we might care about is it well formed, right? Do all the does it make sense? I shouldn't have like 2 plus operators in a row, right? that would be nonsense in the arithmetic world, right? So is a syntax well formed? That's a semantic question, which is an interesting little point. Like the syntax and symbols are all there, but the structure kind of lives in both worlds, right? To be able to, like, you can add structure and that kind of exists in the land of syntax, but evaluating whether or not an actual program is syntactically well formed slowly creeps into the semantic domain. And it kind of lives in this weird gray area between the two worlds. That's all we'll talk about semantics for now. Let's revisit the syntax. How might we formally describe the syntax of this language? Any ideas? As a hint, it's something we've slowly gotten used to using over the last few weeks. Yeah, Maddie. Yeah, so the order, not sort of, that's a part of it. But how would, I want to write the syntax down on paper. What might I use to do that, right? And give it kind of, you know, define it, right? So let me kind of rephrase the question. Have we worked with anything we could think of as a language so far? We kind of defined a language for Booleans, a language for lists, a language for numbers, right? But they weren't kind of self-contained. What did we use to say define the numbers? And the Booleans, what was that called? We define them as types, right? As data types, right? Or in the form of a grammar is the other word we use. So using a data type. Now you can kind of see where the word grammar comes from. It's the grammar of a language, right? That's why these are kind of interchangeable. So let's try and define this arithmetic language. We can, oh, go ahead. Somebody have something? Maybe not, stop me if you do. Let's try and define this grammar, right? For the arithmetic language. We'll call the type expr. We'll throw our nice little definitional equal sign there. Expr stands for expression. Okay. These are arithmetic expressions, right? We'll often use expr throughout the semester just as a shorthand for this is an expression in some language. We're trying to express ourselves, right? In arithmetic. Now, if I'm trying to give constructors for this, what do I need to include? What's in the syntax? Right, we had our operators and our numbers, right? So how might I define a constructor for, say, the numbers or an operator? Let's take addition, for instance. So whenever I create a constructor, I need to give it a name. So let's start with like plus, right? And what does plus take as arguments? Be careful, because we're not in the world of functions here, really. We're trying to write a grammar. So like, what's the form of this, for instance, 5 plus 5? What should plus take? So like 2 natural numbers? Okay, but then what about the case where I have 5 plus 5 plus 5? Something like that. This isn't a natural number, is it? I mean, maybe, but what about, say, what if I want to do something like 5 times 5?
Well, I mean, 5 times 5, do you see the natural number?
It does, but now you're thinking in the world of types and doing like giving these types in a type checking system in a kind of meta level. We're not quite there yet. So I'm seeing an answer I like in chat from Brian that's almost right. So instead of trying to make the constructor plus with taking natural numbers, we can just give it expressions. So let's give it 2 expressions instead. Okay, this will allow us to nest everything pretty much as we want, right? So if I wanted to create, say, an instance of this, I could do, plus, and then plus takes some arguments, right? And say plus takes another plus operator with something inside it, and another plus operator with something inside. Like that's legal syntax now. So I can nest my addition as much as I want. Yeah, so how might I do, so right now I just have this plus operation, but I'm missing something. What else could I add to this? So I've got an operation, but what am I missing here that's really important? Say I want to express actually 5 plus 5. Right now I could only write plus. What am I missing? No equal sign here yet. I'm missing other operations, but just in this expression, what am I missing? I can't actually write that right now. Yeah, so pseudo says numbers. I'm actually missing the numbers, right? So let's add a constructor for numbers. I'm going to call this num. I think that's a good name for it. What should num take as an argument? Just a natural number, right? It's just kind of wrapping up natural numbers and putting it inside our language. Okay. So now if I wanted to say, right, 5 plus 5, I could write that as plus num, and I won't write all the successors out, but num 5, I'll use the shorthand, and num 5. How's that?
We wouldn't need to rewrite the plus
After the or. What do you mean?
You know, we did EXPR is plus expression, and then or, and then and my mom makes us have another plus down there, so we don't need that.
No, because here we're defining the form, right? So it's saying, expert can take the form plus expert, or it can take the form num n. Both are expressions. I don't need to put plus there because plus is kind of, you're never going to have a num with a plus inside it, right? Okay, what else am I missing from my expressions? Let's say I want to multiply minus, multiply minus. Let's add that, right? Make a nice little cozy language. So what should we start with? Let's do multiply. We'll call it mult. What should mult take? Any thoughts on its arguments? Yeah, 2 more expressions, right? Okay. What else do we say? Minus? What should minus take? Yeah, two more expressions. Okay, and we'll leave the language alone here. So we define the form of all these expressions now. Now I can write some pretty gnarly expressions. So let's say I want to write 7 minus 2 plus 3. I could write that. So what's the outer operation? It's minus. Okay, minus will take a num7 as the first part. And then the second part, well, we have a plus operation, right? We write it in line or in fixed, but really it kind of lives on the outside. It's the outer thing. So we also have a plus with num2 and num3. Okay. This isn't really any different than how we defined lists before, like with cons or the maybe type, or even the numbers. These are just constructors at the end of the day. Okay, so we're just building up more and more stuff from scratch. Ooh, Brian has a good point. So I guess we're not going to define parentheses. Do we need to? This is an interesting thought. Do we need to define parentheses? So yeah, so Linnea says, you know, we should probably define some order of operations maybe. I'm going to say that that'll kind of not really be necessary here. Yeah, so pseudo, I think, mostly gets to the point. This language is based on a language that already has parentheses in it. That's almost there, right? But we're not kind of, that's partially right and partially not right. So there isn't anything called parentheses here. Actually, the grammar kind of enforces the ordering for us. So when I write plus, or actually that's not really a good, let me come up with a better example. So something like 7 minus 5 minus 3, this is ambiguous, right? This is when we need order of operations. That's not how you spell ambiguous. How do you spell ambiguous? U-O, like that? Oh, that looks right. Okay. Cool. So like, what could this equal in good order of operations and bad order of operations? Well, this could be 7 minus 5 first, right? Which gives me 2. Minus 3 is -1. And we don't really have anything for negatives yet, but pretend that's not an issue for now. Or if I did this first, I have 5 minus 3, which is 2. 7 minus 2 is 5. Right? Did I do that right? Cool. So it could be -1 or 5. Which one is it? Right? So in arithmetic, we have to write parentheses. Otherwise, you kind of read from left to right usually. But in this language, we have an added benefit. So let's try and convert this into our formal syntax, right? This minus plus the constructors, right? So I could write minus num7, and then another minus num5 and num3. That's one way I could write it. Or I could write the other way, minus yeah, then another minus num7 num5 you know, that's where the parentheses are on the other way, right? Say they're grouped here. And then num3 on the outside. Okay, so just to kind of highlight what's going on there. This is all, bigger highlighter. That's really hard to read. Let's pick a better color. That's not better. So that's all one piece, right? And then here, this is all one piece. So in this syntax that we've given it, the parentheses are already enforced just because we have to group everything in constructors. Okay, there's not going to be any of that ambiguity or need for parentheses. Now, this does bring up a good point. What's the difference between this informal way I wrote things and this more formal way? So we have a word for this. This is an important term to get used to. Concrete versus abstract syntax. And I'll often kind of ask you guys, you know, what's the difference between the abstract and concrete syntax here? The concrete syntax is usually what you're used to programming it. Okay, whereas the abstract syntax is the syntax used by the language designer. Okay, it's more formal, whereas the concrete is kind of more practical. Ergonomics come into play when you're designing concrete syntax, but definitely not when you're doing abstract syntax. And we'll always write concrete syntax, will kind of be in strings, whereas abstract syntax is always a kind of a custom rolled data type, right? Can anyone give a guess? So actually here first, an example. That's actually what I was doing up here. Going between these two, this is concrete syntax, this is abstract syntax. So I'll kind of copy this down. Cool. Any confusion on where this kind of gap separates? Any questions so far? Where was I going next? I lost my place there as I was writing that. Oh, that's it. So this arrow that I wrote here in brown, right, converting between the two. Does anyone know what that process is called by chance? So it's part of a compiler usually. You guys have gotten errors that get this name all the time. So converting between concrete and abstract syntax. Strictly speaking, it's a type of interpreter, but not quite an interpreter. It's not specific enough. Yeah, so Brian comes in again. It's called parsing, right? So when I parse a string, I'm converting it into some kind of abstract syntax. Okay, so when you get a parse error, it usually means you couldn't parse a string, right? Which means that the compiler couldn't take that string and turn it into abstract syntax that it could then go and work on and convert to machine code, right? We'll have the same kind of problems here. I don't know if we'll design a parser this semester or not. I kind of go back and forth. But that's how you go from the concrete to the abstract, right? So that's a piece of the puzzle as well. Can anyone fancy a guess why we prefer using abstract syntax when we kind of do work on languages?
So like what we do is like convincing ourselves that it's correct.
Yeah, so we're kind of convincing there's some kind of correctness idea, right? So some of that comes into play when like the parentheses problem, for instance. What can we do with abstract syntax that we can't quite do with concrete syntax, or not as easily at least? So John's saying there's some notion of generality, not quite here. Can we write functions on concrete syntax? We certainly could. Like if it's just strings, we could write a function that says, okay, when I see a plus sign, do addition, right? But that's really hard to do, partially because of the parsing problem. It becomes really hard to work with that. So instead what we do is we write these things in abstract syntax, and we know how to write functions on those. That's what we've been doing the last 3 weeks is, okay, when I see the constructor plus, oh, do a plus operation, okay? So these all just build up. It's just a buildup of what we've been doing. Now we can define functions over the abstract syntax, right? And define a case statement, right? When I see a plus, I do this. When I see minus, I do this. When I see a number, I do this, okay? What are actually first, any more questions about syntax before we jump into semantics? None in the room. I don't see any online. Go ahead and we can definitely backtrack if we need to. So let's start talking about semantics. So our semantics will be defined usually in 2 ways. One way we'll define semantics is with kind of with functions and interpreters implemented in Scala. And then in the classroom, we'll mostly focus on inference rules, which are more formal. This is what programming language designers typically will use when we're trying to like write down rules for a programming language and then implement them. This is kind of the starting point. So inference rules are the formal definition of a language or of the rules of the language, right? What is an inference rule? Has anyone encountered inference rules before? If you've taken a logic class or discrete math, they might have gotten introduced when you talk about logics. Okay, so these are rules. They've been around for a really long time. So let's do that. These are always in this form. You'll have a big bar, kind of like a division bar, but usually way longer. And on the top of that bar, you'll have some premise. On the bottom, you'll have some conclusion. Another way to think about this, if all of this is true, then this is true. So you can kind of think of them as if then else statements, but there's no else, right? Just if then. We'll often give them a name. So there's a name for each rule. Usually written in parentheses on the side. Okay. Now, what's an example of a rule? So where do I want to start? Is there a better example? Yeah, I guess we can just jump straight into kind of doing this on arithmetic. Why not? We'll introduce some new notation as well. The down arrow, which can also be written, oh, I didn't leave myself enough room. A down arrow B, or actually it'll usually be written E down arrow V. And you can also write it E, more mathy style, V. Is pronounced E evaluates to V. Okay, where E is an expression and V is a value. Have we defined values yet in our language? Like what the outputs are? Not yet. So we can do that really quick. What would we expect our values to be for arithmetic? Yeah, so Linnea says nats, natural numbers, right? So we'll have number values. And I'll define this as a grammar again. So we have a type called val. We'll define it as, we'll have num vals. That'll take a natural number, okay? And then what happens if I do something like 5 minus 7? Is there a way for me to represent that? Or do I have a problem?
Number stuff is zero.
Right, so I can't do negative numbers. How could I deal with negative answers? Let's say I don't want to deal with them. What might I do? Could make them all zero. I don't want to do that either, because that would give me incorrect results eventually, right? Say if I did like 5 minus 7, and that was nested inside something, that would be that would give me a really nonsense error, and I don't want that. It would introduce kind of error in the results. We don't want error in our results. We want correctness in some sense.
Maybe do like they do with like sign bytes, where there's like a 1 on the front of it to mean negative.
I certainly could do that, but I don't want to deal with negatives at all, right? I don't want them to even be a construct in the language. So what would I do if I don't want to deal with negatives at all, and I end up with a result that ought to be negative. I could give nil back. What's a better way of calling that, right? What is that? Undefined, or is an E word I'm trying to draw out of you with a lot of R's in it, like 3 of them and an O. Errors, right? So let's also add a construct for error. Okay. We won't give it any more details. It's just an error. So if I get a negative answer or maybe an undefined answer, I'm going to throw an error. Okay. We'll support negative numbers later and do the full range of integers in the future, just not quite yet. John, can you elaborate on your question? And I'll get back to it. So now that we have our values, we can actually start to define the semantics of our language, okay? So my initial question is, give us a nice header. Let's try and define what's the evaluation for, say, numval, or sorry, for num. So remember up top, we had way up here, expressions. We had, these are the 4 types of expression. We have plus, num, mult, and minus. So we want every expression we give to have some kind of value as an output, okay? So num n, if I get some number n, that evaluates to what? And I'm going to put a bar on top. Okay. Num n evaluates to what? Is it just n? I need a value here. You're cutting a corner right now. Num val of n, right? Yeah. Yeah, we'll try and be extra formal here. Okay. Yeah, and if it helps, look up here at these rules. Remember on the left-hand side, this E is always going to be an expression, that E is always going to be a value. Okay. Did I need anything up top? Any kind of like premise or? Probably not. This is a pretty straightforward rule. When you have nothing on top, it just says this is always true. There are no preconditions that need to be met. No checks that you have to do. If I encounter a num expression, then it's just going to be a num val. Okay, very straightforward. How do we do plus? This is a more interesting case. So, oh, I'll give that rule a name. Always give your rules names. We'll call this eval num. Okay. Now, how do I evaluate plus? Okay, so always start with a big bar when we write rules. I'm going to keep saying this again until it gets hammered in. Big bar for our rules. We're going to call this rule eval plus. So eval plus, I better start with the plus operation on the outside, that constructor. And I have E1, expression 1, expression 2. Another down arrow. And what should go on the right-hand side? What do we think? What were you thinking? Say it.
It's like E3.
Some E3. That's fine by me. We can write that for now. So some E3, but what is E3? Or actually even better, let's call it V. Yeah. These are kind of what it evaluates to, but now we need to say what V is, right? It's, yeah, so V is going to be hopefully a num val. But now I have a problem. What goes there? Yeah, so I added that as a premise, kind of what V is. Well, what we can do here is when I do addition, I need to know E1, it's E1 plus E2, right? That's pretty straightforward, but is E1 a number yet? And is E2 a number yet? What are they? They're expressions. Yeah, I haven't evaluated them down to a number yet, but can I do that? I don't see why not. Wait a second. Can folks online hear me okay?
Yes.
Okay, cool, perfect. Cool, so how might I do that? Well, I have notation for that already. I know how to evaluate stuff. So I'm gonna actually remove our V for a second here because we'll find it's a little bit of a headache to actually write it that way. We'll get back to that idea though. So here we'll write E1 evaluates to some num val V1. Okay, so we read that as a premise for this rule. We know that the expression E1 evaluates to, is computed to this number value V1, okay, as a premise to the rule. We'll often stack our premises, just as a syntactic note on top. So now what can I write? What else do I need to do here? Well, I need to figure out E2. So what might I write there? What could I write there? So I can't quite add everything together yet.
E2 evaluates to num val E2.
Yeah, so same thing for E2. And now down bottom, because I have a V1 and a V2, they're both numbers. I can, as my output, put a num val. And here I'm going to do V1 plus V2. Okay. Now I'm sure some of you are thinking, okay, well, wait, didn't you just kind of rewrite plus there with that, this plus right here? What's the deal with that? So that addition operation is going to be just the addition operation we've defined in Scala, really, right? Or that function that we have. We know how to add numbers together. So this is the plus function. Okay, it's actually doing the computation. Whereas this plus constructor that we had earlier, it's inert. It doesn't do any computation. It's not a function. It's just wrapping everything up in a nice little package. And it tells us, hey, we need to do an addition here, so long as we get two numbers, right? Is there anywhere this could have gone wrong? Or thought in another way, if I evaluated E1, is it possible I didn't get a number value? Okay, Aaron, why? Oh, go ahead, online.
Yeah, this is sort of related to my question earlier, where
Go for it.
the way you have this written is sort of like a logical proposition. But suppose that the thing on top of the bar were false.
Yes.
That would imply that what's on the bottom of the bar were true. Or I guess like logically, false implies true has a truth value of true. So I'm wondering how.
Oh, so you've dug yourself into a little bit of a hole in classical mathematics. where, and stop me if this isn't what you were thinking. We have a law, and sorry guys for the tangent, but this is somewhat important. I'm sure a few other people thinking this, that basically if these two things, the idea is that if these two things weren't true, then this is not true. And that's not necessarily the case. This is called LEM, or the law of excluded middle, which says that either some proposition P is true, P, or it's not true. John, is that kind of what you were thinking?
Somewhat, yeah. Well, yes.
There's a consequence of this, so let me keep
Okay.
going. In this sort of the mathematics that we're doing, we actually reject this rule because of these inference rules. The inference rules here don't adhere to that rule. So if these two things are false, that would seem to imply this is false. That need not be the case. Okay, and actually this isn't quite LEM. This is saying that if I have something like, and this is written more in your discrete math class style, if I had some proposition P imply Q, not P does not necessarily imply not Q. Does that get more to where you were thinking, John?
Somewhat, yeah. I mean, most specifically, I guess I was getting at, like, when we have implications, we can have true values. When we have true implies true, false implies true, or false implies false. So in the case here, if we had a false premise, then our conclusion could not be true. So we see
yeah, so that's actually what I'm rejecting. So say here we could have, say, this be false, this be true, and this could still be true, but it would require us to define another rule that says it's true. So the thing with these inference rules is we're saying this is a proof rule for us to prove this thing is true on bottom, for instance, the conclusion. But I could define other inference rules that make that true, right? So this could be true without these two things being true if I defined a rule to be that. John, let's pause this discussion because it's a little in the weeds. And I think the next rule I define will actually give us a nice little kind of picking up point for that discussion, if that's okay with you. So where were we going with that? So what if E1 doesn't evaluate to a number? What else could it be? So say I still have a plus expression of E1, E2. It's not what I wanted to write. And that evaluates to something. But let's say E1 doesn't evaluate to a number value. What else could it evaluate to? If we're kind of being good about all our cases, what else could it take on? What happens if it's an error? Right, so E1 could be an error. In which case, what should that evaluate to? Probably also an error. It kind of propagates it. We'll call this error plus 1. Okay. What happens if E2 doesn't evaluate to a number? So same thing here. If E2 doesn't evaluate to a number, I'll also get an error. Okay, and now here there's kind of a logical thing going on. I think this might touch a little bit on what John was getting at. Was that I could have said E1 error, but I could have said E1 here evaluates to numval V1. That would be fine. It'd be more specific, right? Because this covers the other case. So I can be kind of as strict, as specific, or as general with these rules as I want. Because we're trying to aim for generality, I'm going to leave that off. But it captures the same thing if we think about these rules in a collection, right? So the rules all live with each other. Any questions about these rules so far? Okay, so now I have a question. We've got 4 rules, and tomorrow I'll kind of sum these up in a little bit of a nicer way and have them so we can always see them. What does, let's say, plus num5 num2 equal? What does this evaluate to? How can we figure that out? Well, we can go look at the rules. Yeah, so, and before we go look at the rules, a couple questions popped up. So Linnea asked, are these like our cases in Scala? They are a lot like cases in Scala, where some of them can be kind of generalized and less specific. Some can be more, and they still capture kind of this larger framework. These are always going to be convertible to functions. In general, inference rules are not always convertible to functions. Sometimes you have to have like a default value. You don't hit every case, and that's okay for inference rules. They don't have to be. We will always define them completely in class. Pseudo, which above part? So pseudo asks, do we not need both E1 and E2 on the above part? Oh, above the line. Correct, we don't. So for these, E1 and E2 don't both need to be present up top, because remember how we read this. I read this as plus E1, E2 evaluates to error if this is true. Okay, so to have E1 up top isn't really necessary. I could put it up there, but I don't really, I could say like E1 evaluates to say V, right? But I don't need that there. I could put that there, but I don't need that there. Yes, Linnea, perfect. It would be more specific than we strictly need it to be. Cool, I think I hit all of the questions there. If I missed something, retype it for me, but I think that covers it. So how do we evaluate this piece right here? Well, we can go look at the rule for plus, right? So what does plus evaluate to? Well, we know plus will evaluate to error, or numval v1 plus v2. How do we figure that out? Well, we can start looking at the premises of the rules. Okay, E1 evaluates to numval. So now I need to start looking at the inner expressions, right? So what does num5 evaluate to? Numval 5, right? That's a value. And what does num2 evaluate to? That's going to be numval 2. Okay, and that's another value. Okay, these weren't errors. And so now we can go look at our plus rule. Well, we have values for V1 and V2. If I have values for V1 and V2, then my output is what? Based off this rule. What should I have? I have a numval, what did I say? 5 and a numval 2. What's the result of the whole plus? Is it just 7? Numval 7, right? I'm gonna be really pedantic about that. It's really important we don't goof that up, because when you go and program in Scala, it'll give you trouble. So move this all over a little bit. And we have a result of numval 7. Question about how I got that? It just follows from the rules, right? We'll use these rules all semester to define the semantics of our language. It's pretty cumbersome off the bat for arithmetic. It's really overkill. Like the functions were a much better way of defining this. But we'll find later that this is actually a really natural way of presenting these inference rules, especially when you start talking about type checking and you can implement those as rules as well. It's just a very good general framework for defining these things. So bear with it for a little while, get used to it, and later it'll seem natural for doing this. Right now it'll feel a little like gross. We just learned how to use functions. Why are we doing this? Give it a week or two, and it'll feel a lot better to use. We got 10 minutes left. I don't quite have enough time to jump into the next thing I want to do. So I think let's leave it at that for the day. Next, we'll kind of pick up with maybe how do we add variables to this language. We'll talk a little bit briefly about how we do multiply and minus, but it's very similar. Yeah, and we'll pick up kind of there tomorrow. So how do we extend this language? How do we add maybe variables to it? We'll pick that up tomorrow. So otherwise, have a good night, everybody, and I'll see you tomorrow.
Professor,
Thank you.
Professor.
Yes.